All right, so on your paper, you're going to use your own paper. We're going to call this exponential models. So section 4.6. All right, and as we go through, I'm going to give you guys some different types of formulas that you're going to need for this lesson. They're all just a little bit different. Some of them we've talked about before, some of them we haven't. This first one we haven't really talked about before. It is going to be the general growth and decay model. And I'm going to call it F of t just because that's what I wanted to call it. It could be called a lot of different things. And it's going to be A, B to the t. And then A is going to be the initial amount. And T is going to be time, and it changes from problem to problem. So like this first one we're doing, time is in minutes, and then the second one that you'll do for homework, time is an hour. So it just depends on whatever is given to you in the problem. And then the base, so like for example, if after 1 minute 80% of the original amount was left, then that base would be 0.8. Or if the material grows by 20% each hour or whatever, then that base would be 1.2. So it has to do with how quickly something is growing or decaying. All right, and a lot of times we have to find that base. Like it's not given to you, you have to find it. So let's look at this number 1. You go to the doctor and he injects you with 13 milligrams of radioactive dye. After 12 minutes, 4.75 milligrams of the dye remain in your system. To leave the doctor's office, you must pass through a radiation detector without sounding the alarm. If the detector will sound the alarm whenever more than 2 milligrams of dye are in your system, how long will your visit to the doctor take, assuming that you were given the dye as soon as you arrived and the amount decays exponentially? Okay, so we're going to use this general formula. And are we given any of these things already? Yeah, we know the initial amount is 13 milligrams. Okay, so out of the variables in the problem that we need to solve it, that's the one that we're given. But we're also given some additional information to help us find B. And that is actually, I'm going to write it as an ordered pair. So after 12 minutes, 4.75 milligrams remain. So 12 is a T, and 4.75 is a F of T. So what we're going to do is take those things and we're going to plug it into our function, and then we can figure out what B is. All right. So I'm going to need to divide by 13. Okay, and we get a decimal that continues forever. So I'm going to write a lot of decimal places. Okay, so how do I solve this for B? 12th root, yes.
Square root. It's not right.
All right, so I'm going to show you how to do the 12th root in the calculator.
Which one is cube root?
So cube root is just number 4. If you hit math and then number 4. Now for the 12th root, if you have an older calculator like these yellow ones, you have to hit 12 first, I think, and then math, and then choose number 5. Now, if you have your own calculator, that's one of the newer ones, like maybe the CE or something, I think you can just go to math, choose 5, and it gives you a little box that you can type the 12 in. But I think on these, you have to do.
You can do the cube root and then arrow over it. Just change
No, it won't let you do that.
Change
I think it gives you an error if you do that, but I'm not sure. You could try it.
What's cube root? 8. Yeah, no, it doesn't get 2.
Yeah.
So it's,
All right, so whatever decimal you just got, you can either like hit second answer, so second x or second and then the negative key, or you can retype it to a lot of decimal places. It's up to you. That's what you should get. Okay, so that means that our base is 0.9195. So each minute, 91.5% of the previous amount of dye is in the system. So if this is ever less than 1, then it's decaying. Okay, so let's just put that in. Okay, so the question is, if you have to have 2 or less milligrams of dye in your system to be able to leave, how long is your doctor's visit going to take? So what do we put that to? Yeah, N for F of T. And then we need to solve it for T. It's been a little while since we solved exponential equations. We just finished the logarithmic. We had to remember how to do exponential. So I really need to solve for that T. What would y'all do first? Very good. Divide by 13. All right, I think this is another one where you get that ugly decimal that continues forever. So we're just going to go to a lot of decimal places. Okay. And then how do I get that T down? We can't do a root for it. There is something we've been talking about for a while. We're going to do logarithm. So if you take the logarithm of both sides, we can use that exponential rule and bring that T down. So when we did this before, we did the natural log. There's a natural log button in the calculator. It's really easy to use. Someone in my last class was like, why can't we just do log? And you definitely can. It's the button that's right above it. It doesn't matter. Okay, so now I can use that exponential property and bring down that T in the front of the logarithm. Okay, and then finally, to solve for that T, we're just going to divide by that logarithm. Okay, so that is in my calculator, so I'm gonna use it in just a second. So do you guys remember how to get that fraction button?
y.
Alpha y equals, right. Alpha y equals number 1. All right, so I want the natural log of that thing right there. So I can go up and choose it if I want to. Or I can do the answer. So answer is second and negative, and it's just as fast. It doesn't matter to me how you do it. And then the natural log is 0.9195. So natural log is just right beside the 4. Now sometimes it matters if you close the parentheses and sometimes it doesn't. So I'm just going to go ahead and just close them every time. In this case, it actually didn't matter, but it's a lot to keep straight. Okay, so that means your doctor's appointment only has to last 22.3 minutes. So you probably will wait longer than that just for your test. The logarithm? Natural log is right beside 4. Yes, ma'am. All right, so it looks like it's going to be 22.3 minutes. So you better hurry up and do that test real quickly, or all the dye's going to be out of your system. All right, then we did talk about, like, back before Thanksgiving break, we talked about the half-life formula. So I'm going to remind you of it. Bless you, because it's been a little while. So all radioactive material decays over time, and they are assigned a half-life, which is how long it takes for half of the original amount to be left. And I think when I taught it the first time, I might have called it Q. I'm going to call it G today. It doesn't matter. So G of T is equal to A, and then in parentheses, 1/2 raised to the T over K. Right? And just like the previous formula, A is the initial amount, and K is going to be the half-life. Now, some radioactive elements, the half-life is in years. Some it's in minutes. Some it's in hours. So it just depends on how quickly the material decays or how slowly.
Why don't they just call it a full life?
Well, because some of it will always remain. It won't decay to 0. There'll always be some remnants of it. All right, so for number 3, the half-life of radium-226 is 1,590 years. If a sample initially contains 200 milligrams, how many milligrams will remain after 1,000 years? So because we know this half-life formula, this problem is easier. Like, there are other ways to do it, but using the half-life formula makes it way faster. So we do know the initial. And I'm going to put T there for now. And then the half-life is 1590. So what are we going to do with that to figure out how much is left after 1,000 years? Okay, we're going to put 1,000 in for T. Okay. And you can just type that straight in the calculator. To get the exponent, you use this little caret, which is above the division. We are running a little low on time, so you can try to do that real quick. But when I did it earlier, I got 129.33 milligrams. Still a whole lot left after 1,000 years. Okay, number 5, we have the half-life of erbium. I think that's how you say it. 165 is 10.4 hours. So it decays way faster than radium. After 24 hours, a sample still contains 2 milligrams. What was the initial mass of the sample, and how much will remain after another 3 days? Okay, so I'm going to go ahead and put in what I know. I do not know the initial amount, but I do know the half-life is 10.4 hours. Okay. And then just like the first example, we are given some additional information that we can use to find what's missing. And so they told us that after 24 hours, 2 milligrams remain. So that's a T and that's a G of T. Now it's important that if your half-life is in hours, what you plug in for T also needs to have the same unit. It also needs to be in hours. So if they told you 2 days or 1 day, you would have 20. You need to change it to 24 hours. 2 days, you change it to 48 hours. Okay, so let's put that stuff in and see if we can figure out A.
You can't use a variable, right? Because it's use it that like selects it or whatever the previous.
Yeah. But you can take 1/2 and you can raise it to the 24 over 10.4. Let's just do 0.5. So that should be your coefficient for your A. Okay, and to figure out the initial amount, we're just going to need to divide by that. So I got that the initial amount is approximately 9.9 milligrams. Right, so that's the answer to the first part of the question. And then it also asks how much will remain after another 3 days. So I'm going to go ahead and just write my formula. So am I going to put 3 in for T? No. Go ahead. So we're going to find G of 72. All right. And so to stay on time, I'm going to tell you guys you should get about 0.0816 milligrams. So it's almost gone, but it's still hanging in there. A little bit left. All right, and then we're going to do 7, and we're going to move on to a different type of formula. So 7 says that a scientist begins with 250 grams of a radioactive substance. After 225 minutes, the sample has decayed to 32 grams. Find the half-life of this substance. Okay, so I'm going to take my half-life formula and put in what I know, and it's really just the initial amount. But we are given additional information we can use to find the half-life. And that's going to be the ordered pair. What do you guys think? What's the ordered pair? So it should be 225 and 32. So that's our T, and that's our G of T. So we are going to solve this for k. What would y'all do first? Good. So the first thing you do is isolate the exponential expression, and that's going to be to divide. And when you divide, this one works out nicer. You do get a decimal, but it's not like a non-ending decimal. It stops at 0.128. All right, and then the only way to get that exponent down is to do logarithm of both sides. And I'm going to go ahead and use 0.5 for 1/2. It just helps us not make a careless mistake in the calculator. All right, and then don't forget, the whole point of that is so you can bring down the exponent. Okay, so there's lots of different things we can do to solve this. I think the easiest way is to think about like that k is in the denominator, but we can't solve for it when it's in the denominator. So if something's in the denominator that you don't want it there, what do you do with it? Multiply by it. So we're going to multiply by k. All right, and then finally we can just divide by the natural log of 0.128. Okay, and that is going to give us that k is approximately 75.865. What should the unit of our half-life be? This one is minutes, yeah. So half-life is always going to have a time as its unit. All right, so bacteria grows exponentially with a base of E. So we're going to do a new formula that is actually the same formula we use for continuously compounded interest. So this is going to be continuous growth. I'm going to call it h of t is equal to a e raised to the kt. A is still the initial amount. T is still time. It just depends on, it can change from unit to unit, depending on what the problem's talking about. And then K is going to be the rate of growth. All right, so for 11, a bacteria culture initially contains 1,500 bacteria, and it doubles in size every half hour. Find the size of the population after 2 hours and after 100 minutes. So if it doubles in size, that does not make K 2. That is not what that means. So we need to find K. But one thing we know already is A. And then we also know an order pair is given to you in a weird way. But it tells you this doubles in size every half hour. So 30 minutes, how many bacteria should there be? 3,000. Good. So 1,500 doubles. So this is a T, this is a H of T. All All right, so in for t, I'm going to put in 30 minutes. And we're going to solve that for k. Just like all of these, the first thing we're doing to solve them is dividing. All right. And then I told the student in my previous class that you can do regular log and not natural log in the calculator. But on this one, because the base is e, we want to do natural log. It makes it way easier. So we're going to do the natural log of each side. All right, so what is the natural log of e to the 30k? Just 30k. Right, and then we can use our calculator to figure out k. So you do natural log of 2, and if you're not doing alpha y equals, you would close the parentheses on the 2, and then divide that by 30. I'm going to go ahead and tell you that you get 0.0231. Okay, so now I have all the things I need for my formula. Once I get my formula all set up, then I can plug in values for t and figure out how much bacteria there is. Right, so the A part of this problem asks us for 2 hours. So do I put 2 in for t? No. 120. So I used 30 minutes. So everything has to be in minutes. So it's going to do we'll do 120. Okay. So let me show you where the E button is in the calculator. So E is it's blue right above ln. So if you hit second and then ln, you'll get E raised to a power. Right, there's also a E that is above the division, but this one always gives you an exponent, so it's a little quicker to use. So I'm just going to tell you what you get since we are short on time. 23,700 bacteria. Right, and then we put 100 in. Is this 100 minutes? Yes. We are going to get 14,961 bacteria. And then the last formula we're going to talk about today is the compound interest formula. And it's one that we've already talked about this year, and you learned about it in Algebra 2. Okay, so it's A of t is P, which is principal, and then in parentheses, 1 plus R over N, and then it's raised to the NT. P is initial investment, R is interest rate, N is number of times compounded per year. And then T, in this case, has to be in years. So time in years. All right, and we're going to do 15. So 15 says to find the time required for an investment to double in value if invested in an account paying 3% compounded quarterly. All right, so A of T. We're not given a value for an investment on this, so we can make one up. And if you're going to make one up, the easiest one to make up is just 1. You invest $1. All right, and then it's going to be 1 plus. What are you guys going to put in for r? It should be 0.03. And then what's in 4? Because it's compounded quarterly, and it's raised to the 4t. All right. So if I want this $1 to double, what do I want it to be? $2. Now, do I need that 1 in front of the parentheses? No. Okay, then I'm going to do 1 plus 0.303 divided by 4. That's going to be 1.0075. All right, so we have an equation now that only has one variable, just t, and we can solve it. So what are we going to do? Take the natural log. All right, and the whole point is so we can take that 4t and drop it down. All right, and then to solve this for t, we're going to divide by 4 natural log of that decimal. Okay. And then on this one, it would definitely be a good one that you did alpha y equals. Just because you're dividing by a couple of different things, your calculator can get confused depending on how you type it in. But this is going to be 23.19 years. Do you think it would have worked out differently if we invested $1 million instead of 1? Do you think it would take longer or shorter for $1 million to double, or the same? It should be the same, because when we do if this was, even if we said it was 100, this one would be 200. As soon as you divided, you'd get 2. So that's how long it takes every amount that you invest to double in this account. Okay, so you are going to have some problems to do from this same page. And I know, looks like most of you, except maybe one row, doesn't have a graphing calculator. You don't necessarily have to have a graphing calculator to do this. You're just going to need a calculator that will do logarithms and roots. I think this first one is the only one you have to do like a weird root. Like we had to do the 12th root on the first one. So you might want to get number 2 done before you leave. But then all the rest, like a normal scientific calculator, the calculator on your phone, if you turn your phone sideways, I'm pretty sure it does logarithms. You just might have to be careful typing it in and closing parentheses and stuff. But anyway, I'm going to give you time to work on this tomorrow also in class. But I'm also giving you a review for your test tomorrow. So the more you have done, the better. I feel like I'm rambling. The test is on Thursday.